we are going to talk about how wings work. What we talk about here is going to be a similar approach to how you will think about how bird wings work, bat wings, even how kites fly. So here is a cross-section of an airplane wing. Airplane wings are designed so that the airspeed above the wing is greater than the speed of below. So we've got our air coming in up here, and it has to travel this longer path on top here than it does, we'll draw my arrows, than it does on the bottom down here, okay? But all of that air, because of mass continuity, travels along the top or the bottom of the airplane wing, and they have to meet the same point back here at the same time. So the time it takes the air to travel over this longer path is the same as the time it takes the air to travel underneath the wing. Okay, so the air flowing above the top of the wing has a longer path to travel in the same amount of time. So what we'll call V top up here has to be greater than V bottom down here, the speed at which the air is flowing on the bottom. And so because of that, we know that V top is greater than V bottom. Now, we know from Bernoulli's principle that whenever you have faster moving fluid, you have lower pressure. So on top here, on top of the wing of the plane, we're going to have lower pressure than at the bottom of the wing of the plane, okay? So the pressure is greater at the bottom of the wing than it is at the top. This pressure difference means that there's a net pressure pushing up on the airplane wing, and that's what gives your airplane wings lift, or that's what gives your bird a lift, okay? And so that's the principle for what's going on here. And we are eventually going to derive the lift equation when we're doing this. The aviation students, it should look pretty familiar to you. And we're also going to solve a problem here dealing with an airplane wing. So this is the principle of what's going on here. So for this problem, we have an airplane with wings, each of an area of 4 meters squared. So the area for each wing is 4 meters squared. Okay, but an airplane has 2 wings. And these wings are designed so that the airflow over the top of the wing, V top, is equal to 245 meters per second, and the airflow underneath the wing, which I'll call V bottom, is equal to 222 meters per second. We're going to find the mass of the plane, M plane, equals question mark, such that the lift on the plane will support its weight. So we're looking for the mass of the plane such that the lift force on the plane equals the weight of the plane. Okay? Assuming that the force from the pressure difference across the wings is directed straight upward. So that our pressure difference, which is going to give us a force, our lift force, is directed straight upward, not off at some angle. It probably in reality is going to be off at some vector angle, but we're going to assume that it's just straight upward here. For simplicity, those are one of the assumptions we have to make in our physics problem. All right, so where do we start first? Well, let's start with Bernoulli. Let's start with Bernoulli's equation. So we're going to do Bernoulli's equation. We need the pressure at the top of the wing plus 1/2 rho V, which is the velocity on the top of the fluid flowing across the top of the wing squared, plus rho G, I'll call it H top, okay? Some vertical distance up here. And then that has to equal the pressure on the bottom side of the wing plus 1/2 rho V bottom, the speed of the wind on the bottom of the wing squared, plus rho G H bottom. Okay, now what can we do? Well, we can assume that the density is the same on the top and on the bottom of these. We're also going to make another assumption that the difference, so what we really care about here is the difference in height. between the bottom of the wing and the top of the wing here. And we're going to assume that this distance is so small, the difference between the bottom of the wing and the top of the wing is so small that it's not going to make much of an impact on the scale of our Earth's atmosphere. And so we're going to say that these two terms here, rho GH top and rho GH bottom, are essentially equal to each other. Okay, so that's one of the assumptions we have to make here. Okay, in order to solve this problem, they're going to be essentially the same, both of those quantities, because the difference in height between the top and the bottom of the wing isn't going to be very large compared to the scale of our atmosphere. Okay, so we can cancel out both of those terms. So now we know that the speed on the top is greater than the speed on the bottom. So if these two terms have to equal each other, and the speed on the top is greater than the speed on the bottom, that means that the pressure on top has to be smaller in order to compensate, okay? So the pressure on the bottom is greater, and the difference between the pressure on the bottom and the pressure on the top of the wing is what's giving us lift. So we're going to solve this equation for P bottom minus P top, okay? So if I go P bottom minus P top equals, I subtracted P top to this side, so I have to subtract this term to the other side of my equal sign. So this is equal to 1/2 rho V top squared minus 1/2 rho V bottom squared. Okay, and then I'm going to call this delta P, the change in pressure. And this is going to equal to 1/2, and I'm going to factor out the density here because they're the same for both terms. V top squared minus V bottom squared. That's our difference in pressure across the wing. That's what's helping us get this lift on the plane, okay? And so if I go ahead and plug in these quantities, V top is 245 meters per second. V bottom is 222 meters per second. We're going to use density of air equals 1.29 kilograms per meter cubed. We plug in that here for density of air. Then we find that this difference in pressure is equal to 6.93 times 10 to the 3 pascals. Okay, pascals is our unit of pressure. Now we need the force for lift. So we know that it's this pressure difference across the wing that's giving us the lift force on the plane to lift it up. So we know that pressure is equal to force over area. So if we solve this equation for force, that's our lift force. F lift is equal to this change in pressure times area, okay? And so then that's equal to our density of air times the speed on top squared minus speed of the air on bottom squared, all divided by 2, and then we multiply it by the total area of the wings on your plane, the total area of the wings on your plane. So this is your equation for the lift. That's how we derive it, okay? Now, there's also sometimes going to be, well, a coefficient here that is associated with the shape of your wing, what it's made up of, kind of like a drag coefficient that gets to pop in right here too, but we're going to ignore a drag coefficient or a lift coefficient here. It's dependent on the shape of your wing, the size of your wing, what material it's made up of, that kind of thing. How slick is that material? But we're going to assume that this is equal to 1 for us in this problem, this lift coefficient. After deriving our lift equation, we still need to figure out what is the mass of the plane such that the lift on the plane will support the plane's weight, okay? So if we draw a free body diagram of the system, we've got our plane right here. We have to have the lift exactly equal the weight of our plane. Okay, so if we're in static equilibrium in that point where both of these exactly equal each other, so then we would say that the sum of the forces has to equal 0 since they exactly equal each other. So the force of the lift upward on the plane minus the weight of the plane, mg, has to equal 0. We want to solve this equation for the mass of the plane to satisfy this condition that the lift on the plane exactly equals its weight. So then m of the plane is going to equal our lift force divided by gravity. Okay? So if you plug in your quantities here for the density of air, we found our difference in pressure right here. Multiply it by the area of the wings. In this case, 4 meters squared is the area of one wing, but our plane has 2 wings. So for the area of the wing, this is going to be 2 times 4 meters squared. Okay? So you plug that in, you get the lift force acting on the plane, and you divide it by 9.8 meters per second. That gives you the mass of the plane, and it turns out that the mass of this plane needs to be 5.66 times 10 to the 3 kilograms. So we've used this principle as applied to an airplane, but you could apply it to anything that has wings: a bird, a bat, a helicopter, even a kite.